I will demonstrate how we can accelerate analytics on Azure Database for PostgreSQL Flexible Server using PGDuckDB extension. First, I'll create a new Flexible Server instance. I'll name the server as PGDuckDB demo. I will now enter the required configuration details such as server version and the administrator credentials. Once the configuration is complete, we can go ahead and create the server. This usually takes some time while the platform allocates and initializes the service. The server provisioning is now complete and our flexible server instance is up and running. Next, in order to use PGDuckDB extension on flexible server, we need to enable it at the server level. So first, I'll update the server configuration by adding PGDuckDB to the Azure.extensions parameter. Then we also need to include PGDuckDB in the shared preload libraries parameter. Let's save and restart the server so that the new settings take effect. The restart takes a moment while the server shuts down gracefully and starts again with the updated configuration parameters. The restart is now complete and the server is back online. At this point, PGDuckDB is available and ready to use. Now let's connect to the server using PSQL. Once connected, we simply enable the extension in our database with a create extension query. The extension has now been successfully created. The installed PGDuckDB extension version is 1.1.0 and it internally uses DuckDB version 1.4.3 as its analytics engine. In this demo, I'll show two use cases of PGDuckDB extension. The first is accelerating analytical queries by using DuckDB's vectorized execution engine on data stored in flexible server. For the first scenario, I have already loaded TPCH benchmark data with scale factor 5. That includes about 5 GB of data in line item table, around 1 GB of data in orders table, and about 145 MB of data in customers table. Let's now run a few TPCH queries and compare the performance. By default, DuckDB.force execution is set to off, which means the query runs using Postgres execution. First, we will run the query using standard Postgres execution engine. Let's start with TPCH query 1. This query performs aggregations over the line item table and scans a significant amount of data, which makes it a good candidate to observe analytical execution performance. While the query is running, Postgres is scanning the rows and computing the required aggregates using its traditional execution model. With Postgres execution, the query completes in about 26.6 seconds. Now let's enable DuckDB execution by setting DuckDB.force execution to on, which forces the query to run using DuckDB execution engine. Running the same query again, you can see it completes in 11.1 seconds, which is 2.4 times faster. That's a nice performance improvement, and importantly, we achieved it without changing the SQL query. Now let's switch to Postgres execution and run TPCH query 13. This run completes in 7.7 seconds. Now we run the same query with the DuckDB execution enabled. This time the query finishes in about 4.1 seconds, which is close to 2 times faster. Again, it's a very nice improvement for this analytical workload. Now let's see another example. First, let's switch to Postgres execution. Next, I'll show the query that demonstrates a classical analytical pattern, multiple count aggregations per group. In this query, we filter orders between 1993 and 1996 and then group the results by order priority. For each priority, we compute the number of distinct customer, number of distinct clerks, and number of distinct orders. Queries like this are relatively expensive in traditional row-based execution. With Postgres execution, this query takes 15.7 seconds on this dataset. Now let's run the same query using PGDuckDB execution. Here DuckDB processes the data in vectorized batches, which allows it to apply vectorized aggregations very efficiently. This time, query finishes in 2.3 seconds, which is nearly 7 times faster. That's a significant performance gain without changing SQL and without moving the data out of Postgres. Now let's move to the second part of the demo, where I'll show how to read and write Parquet files stored on Azure Blob Storage directly from Flexible Server using PGDuckDB extension. To allow DuckDB to access files in Blob Storage, we first create an Azure Storage secret. In this step, we register our Azure Storage credentials using the create Azure secret function. Once this secret is created, PGDuckDB can securely access files stored in our blob containers. For this demo, I'm using a historical stock trading dataset stored as Parquet files in the blob storage. Let's first quickly read the dataset using read Parquet function. This simply verifies that the Parquet file is accessible and gives us the preview of the data. Now let's run a slightly more interesting query. Here we query the same Parquet file directly from the blob storage and retrieve the 10 trading entries with the largest price movements. What's important to notice here is that the data remains in the blob storage, Flexible Server does not ingest or load this dataset, and DuckDB scans the Parquet file directly and returns the analytical results. The next part of the demo demonstrates hybrid analytics, where we combine transactional data stored in Postgres and analytical data stored in Azure Blob as Parquet file. Let's start by creating a small Postgres table to represent a portfolio watch list. Let's insert a record for a stock we are monitoring. This table represents operational or transactional data that typically lives in Postgres. Now for the interesting part, we take the watch list table stored inside Postgres and the latest closing price from our Parquet dataset in the blob storage and join them in a single query. That's a result. So we are effectively combining operational database data with external analytical data stored in blob storage, all through a single SQL statement. No ETL pipelines, no intermediate ingestion step, and no data duplication. That's a really powerful capability for hybrid analytical workloads. Finally, let's write result back to the Azure Blob storage as a Parquet file. And here we see that the file has been created. And let's also see that the content of the file by reading it using read Parquet function. And here is the data we have written. That's awesome. Postgres can read external Parquet data, analyze it, combine it with external tables, and then write the results back to the Azure Blob storage. We can seamlessly analyze large data sets stored in Azure Blob storage, combine them with transactional data in Postgres, and produce analytical outputs all using standard SQL. That's a powerful analytics with PGDuckDB on Azure Database for PostgreSQL Flexible Server. And this capability is now available on Flexible Server versions 14 through 18. I encourage you to explore it and see how it can simplify analytical workloads and accelerate analytical queries on Flexible Server. Thank you.